In this video, I will talk about trigonometric functions, specifically focusing on the unit circle. The objectives of this lesson are identifying a unit circle and describing its relationship to real numbers, evaluating trigonometric functions using the unit circle, and using domain and period to evaluate sine and cosine functions. The two historical perspectives of trigonometry incorporate methods for introducing the trig functions. One such perspective is based on the unit circle. So we consider the unit circle to have a radius of 1, and it's represented by the equation x squared plus y squared equals 1, where x and y are x and y coordinates. And then the center of this circle, it's going to be right here in the middle, 0, 0. So we're going to be using this for our trigonometric work. So what we like to do in this slide is to form any type of angle and focus on the side lengths. So what I'm going to do is using this initial side. So this one is my initial side. And you guys realize this happens to be my radius r, which seems to be 1 unit. And then I'm gonna form an angle that looks like this. So this thing is now my terminal side because I ended up being there. So terminal side, and then this angle, let's call it theta, okay? Let's call this angle theta. And then what happens here is that this angle will have a point on the circle. So let's call that point on the circle to be x, y, where x represents the x coordinate of this point, y represents the y coordinate of this point. And specifically what this means for us is, I'm going to illustrate with a color here. So x is going to be what it corresponds on this x-axis. So x is basically this distance represented in red. And then y is going to be the correspondence point on the y-axis, which is the distance represented in purple. Or I'm sorry, it's gonna be represented. I should do the opposite, but what I meant is y is right here, and that y is gonna be this height. So this is the height y, and then x is that distance on the x-axis. All right. So another way of another language that we use to represent this situation is that for x, as I called it previously, I'm going to call x, that length for x, I'm going to call that to be horizontal distance. So horizontal distance of my point from 0, 0. And then the y coordinate is going to be my vertical distance. So again, these are all distances from the center, or 0, 0. So using these ideas, I'm going to form the idea of trigonometric functions. So I'm going to use x and y and then use that to form trigonometric functions. All right, so it follows that the coordinates x and y are two functions of the real variable t. And I'm gonna show how each of these 6 functions are formed in the next slide right here. So the definition of trigonometric functions. Let t be a real number. T might seem to be confusing for you, but what t is the measure. T is the measure of an angle on a unit circle. Okay, so this is just a measure of an angle. So based on this, we're going to let x comma b the point on the unit circle corresponding to t. So think of this as something like we have a unit circle that looks like this. We have a point here, x comma y, and then that angle is going to be t. So the measure of that angle is t, and then x comma y are the distances of that point from 0, 0. So based on this information, we're going to let sine to be y. So it's just going to be sine, which is the vertical distance. So this guy is always my vertical distance. And we define cosine by x, which is the horizontal distance. Horizontal distance. And then to see this on the graph, as I previously showed you, this side of this is x, and then this height is gonna be y. So, and y happens to be the sine of t, and then x happens to be sine or cosine of that angle t. And then based on this information, we define tangent, which is always y equals y over x. So the ratio of vertical distance and horizontal distance. Cosecant is defined by 1 over y, so 1 over the vertical distance. And secant of t is defined by 1 over x, which is 1 over horizontal distance x. And lastly, cotangent is x over y, which is going to be the horizontal distance divided by vertical distance y. So all these functions are based on this definition. So we're interested in all these 6 functions and what they do. And in the future, we're going to be talking about their graphs, all their domain and range, all the cool features about these functions. All right, next thing we're interested in is we're interested in some actual values. So what we like to do is we like to divide this unit circle into 8 equal arcs. So we divided it into 8 equal arcs. So what that means is that from an angle perspective, we're going to realize that because we divided 8 equal parts and we know that one angle has 360 degrees or 2 pi, then each of these things that we have, because we're dividing it into 8 parts, so what that would mean is that each of these parts will have the angle 360 divided by 8 degrees, which would be something like pi over 4, which is 45 degrees, or 2 pi divided by 8, which is pi over 4. Okay, so what we say is that, for instance, for this point right here, what we're doing is we're just going angle pi over 4. Or if you want to do this other one, we're going to do this way. We're going to do 2 times pi over 4, which is pi over 2. And then similarly, all these guys could be formed by that idea because we're going to realize each of these pieces are 45 degrees. Similarly, we could go clockwise direction as well. So like to go from the initial side to this guy, we're going to do negative pi over 4. From the initial side here to here, for instance, we'll do negative 2 times pi over 4, which is the same thing as negative pi over 2. So negative 90 degrees in other words. Negative 90 degrees in other words. So using that idea, you can go either direction, either left or right. Depending on what these angles are, you're going to have different things. So the thing we need to realize is for each of these points, for instance, for this point right here, I formed this point using this purple thing right here. I just draw it. So this angle is going to be, we have 1, 2, 3 pieces of pi over 4. so 3 pi over 4. So this is the angle here. And then the point will have the coordinates x comma y to be negative pi over negative square root of 2 over 2 comma square root of 2 over 2. So that is what x and y is. And using that information, we'll be able to figure out some cool things about it. Like we're going to use the trig functions and then work with some numbers. Similarly, we can divide it into 12 equal arcs, right? So we could also do 12 equal arcs. And if you do that, each angle, each little piece will be something like 300 degrees divided by 12, which I think is 30 degrees. Or we can say 2 pi, because 2 pi is one full rotation, and then divide that into 12 pieces, you get what? Pi over 6 radians, right? So each of these little ones will be pi over 6. So for instance, if you do negative direction, like 2 pieces like this, then this angle must be something like negative 2 times pi over 6, which happens to be negative pi over 3. So negative pi over 3 will be the corresponding angle for this point that is represented in red. All right, so one of the things we can do is we can verify points on the unit circle because note that for this point that they specifically pick square root of 2 over 2 comma square root of 2 over 2. I think that happens to be this guy. This realized lies on y equals x because it divides that portion into like two equal pieces. Like this is one piece, this is one piece. So it should lie on y equals x. So substituting x for y in the equation of the circle, which you guys may remember, x squared plus y squared equals 1. This is the equation for the unit circle. You can replace y for x and realize that x is going to be this, square root of 2 over 2. And because x and y are the same, then square root of 2 over 2, comma, square root of 2 over 2. There's other ways of figuring this out. We could also do this idea of right triangle, which is something I'm going to do in the next video. But we could also form a triangle on this unit circle and compute what x and y is. All right, so I'm going to move on to evaluating trigonometric functions. So what I'm going to do is I'm going to evaluate the 6 trig functions at each real number given. So what we're given is, you guys realize all these givens are angles, right? These are all angle, let me write it as angle measures on a unit circle. So these are all angle measures on a unit circle. What I'm going to do is I'm going to evaluate each of my functions at these angles. Okay, so first we're gonna start with the realization that part A, t equals pi over 6 corresponds to the point x equals square root of 3 over 2 comma 1 over 2. So how did we find that? So we're gonna go back to the unit circle, and then I'm gonna find pi over 6 on this unit circle. The way I'm gonna do that, we know that pi over 6 is 2 times pi over, it's half of pi over 3, or in other words, it's one of the pieces of the whole thing, because 360 degrees, or let me use a radian, 2 pi divided by 12 is each of my pieces, which happens to be pi over 6. So each of these pieces are pi over 6. And because I need 1 pi over 6, I'll just go one direction here. Then the point we're dealing with must be that comma x comma y, which happens to be square root of 3 over 2 comma 1 over 2. That's how I located it, because I know each of these pieces in that unit circle is going to correspond to pi over 6. All right, so now I know what x and y are. So what I'm going to do next is I'm going to evaluate each of my functions. So I know that sine is always y, which is the um, vertical distance. So let's go back to unit circle. So the y in this case, and x is what we're interested in. So the way I'm going to find that is, you guys realize this purple is going to be y, because that's the height. And let me use green for x. So let's take a look at what y is in this case. Y is 1 over 2. X is square root of 3 over 2. So that's why when we compute sine, we're just going to take a look at y because sine only requires y. So y in that case is 1 over 2. So that's why sine of pi over 2 must be 1 over 2. Cosine of pi over 2, because we know cosine is always the x, always the horizontal distance, then we go back and realize that the horizontal distance x is square root of 3 over 2. So then sine of that angle must be square root of 3 over 2. Similarly, I'm going to do tangent. So tangent of pi over 6 is going to be y over 6 because that's the definition for tangent. And because we know y is 1 over 2, x is square root of 3 over 2, then that ratio is going to be what tangent of pi over 6 is, which is square root of 3 over 3. Cosecant is always 1 over y, so you're just going to say 1 over 2, which simplifies as something like this, like you divide this by 1 over 2, flip and multiply, so 2 over 1, so then get 2. That's how they get it. For secant, we're always going to do 1 over x, so then because x is square root of 3 over 2, what they did is they did something like 1 over square root of 3 over 2. So then flip multiply, you get 2 over square root of 3. And because we don't want rationals at the bottom, we multiply it by square root of 3 over square root of 3, like the same bottom, to get rid of the bottom rational. So you get 2 square root of 3 divided by 3. And that's what we get right over here. Lastly, cotangent is always x over y. So do the same thing. Replace x by square root of 3 over 2. Replace y by 1 over 2. And then you get square root of 3 as an answer. So this is one part of the example that I did using pi over 6. In the slides, you're going to have example for each of these. So like whenever t or the angle is 5 pi over 4, whenever it's pi, whenever it's negative pi over 3, for each of these, you'll have the solution. But what I want you to do is I want you to pause the video and then for yourself, try to practice computing all the 6 trig functions for 5 pi over 3, and then do the same for pi, and then do the same for negative pi over 3, and then hopefully compare your answers with the solution in the slides. Please pause the video and then do that. All right, hopefully you had a chance to practice that a little bit. Next thing I'm going to talk about in this video is looking at domain and period of sine and cosine functions. So in this video, I'm just going to talk about domain and period of these two functions. So first of all, let me clarify this. We don't use the language of range for trig functions. The reason is that these functions always repeat. Because sine and cosine are cyclic functions, because they always repeat the same behavior, we use the language period. And I'm going to talk about that a little bit soon, but you may be wondering, why did I not say domain and range? That's the reason. These functions are a little bit different than the functions we've seen before, because these guys are periodic. They repeat the same relationship over and over. So here I provided two graphs that you have seen on the Desmos activity that I shared with you. This first one, you may recall, is the graph of the sine function. So this is the graph of sine function, and then here at the bottom we have the graph of the cosine function. Okay, and then we know that the domain of these functions is the set of all real numbers. What that means is for the input x, or input is the angle in this case, could be any real number. Same thing for cosine. You can input any type of angle and get a response. Okay, so the domain of these functions are always going to be from negative infinity to positive infinity. Same thing for cosine. Domain is any real number from negative infinity to positive infinity. So then what we're interested in, the range. So how do we figure out the range? How do we figure out the period? So the way we can figure that out is, you guys realize range is always the y value, right? This is always y value, or the output of a function. That's what range is. So when we look at the graph, the y values we're getting is like, for instance, for sine, we get something here, we get some y value, and then it looks like we have this guy to be the max. And then we have different y values for different locations here. And you guys realize the minimum we have is right at that point, somewhere right here. So then what that means is that the highest y value that this function can take is going to be something like +1. And then if it's not transformed, if it's just a pure sine x, it's always going to be +1, +1. And then it's always going to be -1 for the minimum. And the same thing for cosine function. Highest it's going to take is +1. Minimum it's going to take is always -1. So then what we're going to say is, in general, cosine function is always going to take minimum -1, no more than smaller than that, and highest is going to be 1. And for sine function, it's always going to be the same. It's going to take 1 at most and -1 at least. So we're going to keep this in mind, that it's always going to be that. And then another way of seeing this is using the unit circle. So you guys realize that cosine is always the horizontal distance. So the highest cosine you can have is either this angle or this angle when you have pi degrees. And then all of these have the distance to be 1 unit. So at most, it's going to get that. And then for the sine function, the at most value you get is, because sine is the vertical distance, you're going to either get the highest when it's this case, or it's going to get highest when it's that negative side, where you will still have this one. And again, the length of these are always going to be 1 units. So that's why it's -1 and 1 right here in the given. And for x is the same. All right, so next thing we're going to do is, I told you guys this idea of rotating around angles. You guys remember one full rotation is always 2 pi degrees. One full rotation is 2 pi. But what if you continue doing the same thing? What if you do one rotation and then do another rotation, right? So I might have 2 rotations, and that will be in total 4 pi angle degrees. And you can continue doing the same thing. So you can have another one. What if you do 3 rounds? Then it'll be 1 2 pi, 2 pi. So you get 4 pi's, and then you do another one, then this one would be 6 pi. So, and you can also do the same thing for the negative direction. You can have -2 pi, -4 pi's, -6 pi, and things like that. So you can always repeat, right? So what that means is that adding 2 pi to each value of t, which is my angle, it's always angle, in the interval results in a revolution around the unit circle as given in the below, where you might have things like, if your angle is pi over 2, then you may have pi over 2 plus 2 pi. So like you can have one cycle and come back to that exact spot. And maybe you can do 2 rotations, which would be 4 pi, and then come back to that same angle. I meant to put plus here, right? Or I might have 3 rotations. So then I'll have pi over 2 plus 3 rotations with 6 pi, etc. So I can write as much as I want. The same thing, I could write as much as I want. So for instance, for the degree, for the angle 3 pi over 2, I could do the same thing. I could have 3 pi over 2, or I could have one full rotation and come back to that same spot and do that again and do that again. So it's always possible. One other illustration I want to show you guys regarding this is that, say I have this unit circle, and then my angle right here is, I'm going to use pi over 4 here. So this is pi over 4. So with this Let me write it this way. So with this blue, I formed pi over 4. So someone else might come here and say, well, I'm going to do the same thing. I'm going to start from 0 and then start kind of like cycling around. So I can do 2 pi. You guys can see I did just like one full rotation, 2 pi. And then I might do a little bit more. I might add pi over 2 for that, and then end up at that exact same spot. So what this red line represents is one full rotation plus pi over 4, which is 2 pi plus pi over 4. So you guys realize we end up exact same location, same location. So pi over 4 and 2 pi plus pi over 4 will end up being at the same spot. So here I define all this, and then what we're generally interested in is this result of sine of t plus 2 pi n is always going to be sine of t, and cosine t plus 2 pi n is going to be cosine of t. For any integer n and real number t, you guys realize t is an angle, and what n is the number of revolution. This is the number of revolution, because we know that 1 rev is end up being 2 pi. 2 revs is 4 pi. So then if we have n many revs, then we'll do n times 2 pi, right? Because we know that 2 revs is 2 times 2 pi. If you do n revs, then you should have n times 2 pi, which is represented right here and here. Okay, so here I formally put that definition that you can take a look. One other thing we need to know is that even odd situations, in general, we need to know that cosine and secant functions are even. The sine, cosecant, tangent, and cotangent are all odd functions. And then I'm going to conclude this video by looking at this particular example. So like I was telling you guys earlier, these angles might be bigger than 1 revolution. So for instance, 13 pi over 6, I know this angle is bigger than 1 rotation because I know 1 rotation is 2 pi. So what I do is I subtract 2 pi from this angle because I know it's bigger than 1 rotation. So it's pi over 6. So what that means is then if I'm interested in, say, the sine at that angle, I'm going to say sine of 13 pi over 6 must be the same thing as sine of 2 pi over 6. And because we know that 2 pi plus pi over 6 and pi over 6 will end up at the same location. Because it's going to end up being at the same location, we don't have to worry about the value. All we worry about is we just compute for pi over 6 because it's easier for us. We know what sine of pi over 6 is. We can use the unit circle to determine that, and then we can say, well, then sine pi over 6 must be 1 over 2. So because we know 7 pi over 2 is again bigger than 1 full revolution, and specifically this is actually 2 revolutions to the negative direction. So it's basically negative direction 2 times 2 pi. That's why we have 4 pi right there. And because we know that specifically it's equal to pi over 2 when we subtract that value, then what that means is that, say if we're interested in the cosine, then what we do is we'll go ahead and do cosine of this angle must be the same thing as cosine of that revolution plus pi over 2. And I know how to compute cosine of pi over 2, which seems to be 0. Again, you look at the unit circle and then determine what cosine of pi over 2 is. That's gonna conclude my video. Thanks for listening.